concept of deadlocks. Deadlocks is relevant to non-predictable resource. Okay.
Yeah.
Do you still remember the predictable and non-predictable resource?
Yeah.
Okay. Deadlock happens when non-predictable resource exists. Okay. These two programs about one process. Yes, only one process. Okay. In the first example, one process wanted to acquire one resource. Yes, this example, one resource and one process. And in the second example, one process but two resources. It means process A must use two resources. Okay, two resources. And then the second example, we can see that two processes. Yes, process A and process B, and two resources, resource 1 and resource 2. And we define a semaphore for each resource. Yes, so there are two semaphores for two resources. Okay. So I think you can read the program by yourself for some minutes. This program, the left part, okay, two processes and two resources. Focus on the lines in the loop. We just compare these two processes, process A and process B, and focus on the lines in the loops. And we will find that these lines
are same.
Yes,
both
are the same.
Both process
yes.
work are same.
Focus on this one. Are the same, okay? Because the first line is two.
Resource 1 is wrong.
It resource 1. It means decrease the semaphore. Okay, the semaphore of resource 1. Then decrease the semaphore for resource 2. Because we decrease these two resources, so we can use both resources. Okay, and finish the task. And then release resource 2, release resource 1. Okay, get resources, require resources, and use resources, and release resources. Okay, and the sequence is the same. Then we will find that first process A, if it is successful to conduct the down operation on resource 1. That is to say, process A successfully get resource 1. Okay? Suppose that process A, we can see that both process A and process B to require resource 1 at the same time. Yes? Because the first line is to require resource 1, okay? And process A all process B will get the resource. Yes, maybe process A, maybe process B. Yes, so we can suppose that process A get resource 1. Okay, and then process B fail. Yes, because process A has get the resource 1, so process B fails in the first line. Then process B will wait. Yes, because process B is blocked.
Yeah.
In the first line is blocked, so process B will wait for resource 1. Okay, and now process A get resource 1. So when process A get resource 1, then process A will get
Resource 2.
yes, will get resource 2. But now process B is still wait for resource. Process B is still waiting for resource. Which one?
Or resource 1.
Yes, because the first line is to add resource 1, but he fails, so just wait. Nothing to do, just wait. Yes, so it means process B is still waiting for resource 1, and now process A got resource 1, got resource 2, because resource 2 is now available. So process A got resource 1, got resource 2, and then use these 2 resources. After process A finishes the task, then release resource 2, release resource 1. Now resource 1 is available, yes, because it is released.
Yeah.
So process B begin to get resource 1, and then because resource 2 is also released, it is available.
Yeah.
Process A has released resource 1, resource 2. So process B gets resource 2 and using resources and release. Okay. So both process A and process B can finish the tasks. Yes, no problem. Okay. Is there any problem? No. Focus on the right part. Focus on the right part. It is also about 2 processes and 2 resources. Focus on this part.
There are 2 processes will work together.
Together
Means they
at
are
the same time. Yes.
Yeah.
Process A and
Because
process B
they are-
run at the same
their
time.
process B is getting resource 1, and in the process B getting the resource 2.
Yes. Now process A, the first line is to get process 1, and resource 1
Resource
is
1.
now process B is to get resource 2,
Yeah.
different resources, and now these 2 resources are available. So process A get resource 1, and meanwhile process B get resource 2. Okay, no problem. Okay, focus on the second line.
When process A going to take the resource 2, that time it's not available.
Yes, but fails. Okay.
Yeah.
Process A now want to get resource 2, but we know that process B has get resource 2,
Yeah.
and the semaphore is there now. Okay. It means this resource is occupied. Okay. So process A will fails at the second line.
Yeah.
Okay. Then process B.
Also failed in the second line.
Yes, also fails at the second line because resource 1 is used by process A. So both process A and process B fails. Process A waiting for resource 2. Process B waiting for resource 1. But resource 1 is occupied by process A. Resource 2 is occupied by resource B. It means that I want to get an item from you, and you want to get an item from me. So there is a deadlock. Okay? I can finish the task, and you can also finish the task. For both neither one. So there is a deadlock. Okay? So there are two programs. The liquid program, there will be no deadlock, but maybe deadlock will happen for the second program. Okay. So I think we have get some basic information about deadlock. Now let's get depth into deadlock. What is a deadlock? Deadlock definition. Deadlock means that a set of processes is deadlocked because these processes want to get some resources. Okay. Processes are deadlocked if each process in the set waiting for an event. Okay? For example, process A is waiting for resource 2 to be released. Okay? The event is the resource 2 to be released. Okay? Each process is waiting for an event, but that event can be caused only by another process. Okay, I'm waiting for you, you're waiting for another person, and so on. Then maybe there will be deadlock. Okay. Specifically, conditions for resource deadlocks are as follows. There are 4 conditions. Yes. The first one is mutual exclusion. We have known mutual exclusion in the chapter of the process. This means a resource is only used for one process, and another process should wait. Okay? Hold and wait. If the resource is held by one process and the other processes should wait. Okay. The third condition is no preemption. We have learned the 2 types about resources. Yes. Predictable resources and non-predictable resources. Okay. Deadlock is relevant to non-predictable resources. The fourth condition is signal wait condition. It means that the relationship between these resources comprise a circle. A waiting for B, B waiting for C, and C waiting for A. Then these relationships comprise a circle. Yes. There must be a circle, okay?
Yeah.
We know how to model a deadlock. That is we use some model to describe a deadlock. Okay. For example, in this figure, In this figure, a circle means a small circle means a process. So this is the process A. Okay, this is the process B. This is the process D. This is the process C. A small circle represents a process, or we can say denote a process. Okay, and a rectangle denotes resource. This is the resource. Resource R, resource S, resource T, resource U. Okay, two items, process or resource. Okay, then there is a line, directed line. Okay, in this figure, there is a line from a resource to a process. The line is from a resource to a process. Okay, it means that process A gets this resource. Okay, if the line is from resource to process, it means that this process now is using this resource. Or we also can say process A gets resource R. Okay, but on the contrary, we can see this line is from
process B.
Yes, from a process to a resource. So these two lines are opposite. The direction are opposite. Okay, from a process to a resource. It means that this process requires the resource. Okay. Okay, again, in figure A, the process is using
the
this resource.
Yeah.
But in figure B,
the process need that resource.
Yes, just want to get the resource S. Okay, so we just focus on figure C. We can see that there are two processes and two resources. So can you tell me the meaning? Can you tell me the meaning of the lines?
In the D process, process D, we have a T resource.
Yes.
And he need U resource. Required.
Yes, process D gets resource T.
Yeah.
But
required
requires
U.
resource U.
Yeah.
It means process D. If process D want to finish a task, process D must own resource D and U. Both D and U. Okay. But now this process D only own T. It doesn't own U, so it requires resource U. Okay. Focus on this one.
This one also. In the process they have the U resource and need the T resource. Require the T resource.
Yes. Process C. If process C wants to finish the task, it must own both T and U. Okay. But now process C owns resource U. It doesn't own resource T. Okay, so process C requires resource T. So T is owned by D, U is owned by C, but D requires U, C requires T. Okay, so we can find that there is a
ideal time for both process.
We can see that these lines comprise a circle.
Yeah.
directed circle. Yes, T to D, D to U, U to C, and C return back to T. Yes, there is a circle. So we can get that from the definition. There is the deadlock. Okay. This is a simple example. Then we may have more complex examples. Now, this is the requirement. Process A requests resource R. Process B requests resource S. This is the resources. These are processes. Okay. A, B, C. 3 resources processing. Okay. How many resources? How many? No, how many? How many resources?
It's 9.
3. R is T. Okay. 3 processes and 3 resources. Okay. So 3 processes and 3 resources. Okay. So maybe we can arrange the resources. Okay. For example, because now A request R, so maybe we can allocate this resource R to A. Okay, so now A get resource R. Okay, because I want to get resource R and R now is available. We can allocate R to A. Okay, so now A get R. Yes. And the second is that B requires S, and now we find that S is available. Yes, so we can allocate S to B. Yes, so now B owns S. The third one is C request T. Yes, and now we will find that T is available. Okay. No process occupies it, so we can allocate T to C. Then C gets T. Yes? C gets T. Okay, no problem. Is there any problem with this figure? Okay. We can see this one. From this request, we get that process A want request R and S. Yes. And process B also want S and this is S and T. Okay. And process C wants T and R. Okay. Because you can see that C requests T, C requests R, 2 resources. It means that each process wants to get 2 resources. Okay? And now we do allocation. Okay? Continuous. Now the first one, and the first is C request R A requests R, A, B, C, R, S, T, and now A requests S, yes, because if A wants to finish the task, A must own both R and S. So now A requires S. Okay.
It's request or release?
Just require S, but now B occupies S. Okay. We will also see that B wants both S and T. S and T. Now B owns S, but B wants T. Yes. So B requires T. Okay. And then focus on C. C requires both T and R. Yes. Now C owns T, but C requires R. Okay. A requires S, B requires T, and C requires R. Then we will find that there is
a cycle.
Yes, there is a circle. For example, from R to A, to S, to B, to T, to C. Then we turn back to R. Okay, there is a circle. So there is a deadlock. Okay, okay. Let's cover this. There will be a deadlock. Okay, maybe we can change our arrangement. For example, we first allocate R to A. Yes, then process A gets R. And the next one we allocate T to C. Then this process gets T. Okay, and the next one, because process A requires both R and S. Yes, so we allocate resource S to A. Yes, this is because we want one process to finish its task. We just select process A. Maybe we can select process B. Maybe process C. And now we select process A, just as an example. Process A now gets both R and S. Okay? It's both R and S. Then process A, the next step is to use both resources. Yes?
Yeah.
Return back, request the resource and use the resource, then release the resource. Okay? Now process A gets both R and S. It can use the resources. Okay?
Yeah.
Then we want process C to use the resources. Process C focus on requires both T and R. Yes. Then now process C gets T. So process C requires R. Yes. This is required because R is now used by A. Yes, A gets R, so C that just requires R. Okay, C gets T. Now process A get both R and S and uses these resources. but C is waiting for R. Okay, it's just waiting for. Then process A finishes task because it gets both resources. After the finishment, process A release R. Yes, you can release R because the task has been finished. Okay, now release R. It means that we delete this line. Yes, just delete this line from the figure. We got the next one. Now R is available and C require R, so we allocate R to process C. Okay. A will also release another resource S. Yes, so we delete this line because process A has finished the task. Okay, and now we will find that process C gets both T and R. So process C begin to use these two resources. Yes. Okay. Process C to use these two resources and finish the task, and then release T and R. Okay. And the next one, we are allocated the resources to process B, and the process B begins to use resources and release resources. Okay. So we will find that. In this assignment, there will be no deadlock. Yes, no deadlock. So from this example, maybe we got this idea. It is complex. Yes, it is complex to make the arrangement to avoid the deadlock. Okay, it is not an easy task, maybe a complex task. So the next one, maybe we should to think more about how to avoid deadlock. How to make the arrangement and no deadlock happen. Okay, this is the next thing we wanted to solve. Yes. So there are, we will get depth into the algorithm, how to avoid deadlock. Okay. 你可以把这个关了。
Priority thread. Now notice that that statement doesn't say that the low priority thread will never run. It just says it's being really continuously unfortunate and never going to run at this moment, but it might in the future. Okay, that's starvation. Deadlock is a very specific type of starvation, which is a circular waiting for resources that will not resolve itself. So a great example here is this sort of resource and thread graph here, where thread A basically is, it owns resource 1, and that's what this owned by arc is, and thread B owns resource 2, which is this owned by arc. And basically, thread A is busy waiting for resource 2 and thread B waiting for resource 1. We have a cycle, it'll never resolve, we're in trouble. Okay, that's a deadlock. It's a circular situation where it'll never resolve. And basically, deadlock implies starvation, but not vice versa. Okay? That clear? Starvation can end, deadlock can't, without something pretty drastic. So usually you have to end up killing one of the threads or doing something drastic to the system in order to resolve the deadlock, because it won't resolve otherwise. Okay. Notice also, you can see something very simple. I encourage you to try to come up with a deadlock with less than one thread. Less than two threads. Less than one thread would be cool. No, less than two threads, because you really need two threads that are circular waiting on each other, or you're not going to be able to get a deadlock. Okay, so two threads involved. All right. Now, what are some conditions for deadlock? Well, Deadlock's not always deterministic, so here's an interesting scenario here, and I'm going to use, just for simplicity, I'm going to use the language of semaphores here, but we have two semaphores, X and Y, which are being used as mutexes, so these are locks that are initialized to 1. And notice that if thread A does an X dot P, Y dot P, and thread B does a Y dot P, X dot P, then, and then we basically finish it off with releasing. This is sometimes a deadlock and sometimes not. Now you can clearly see that if thread A gets to go through its whole thing and thread B never interacts with A, so it's never messing with Y and X at the same time A is, there's no deadlock problem. But I hope everybody can see here that if we happen to be in a situation where A grabs X and B grabs Y, and then A tries to grab Y and B tries to grab X, we're now in that exact cycle I showed you on the previous page. Okay? So this code is really annoying because this gets a deadlock, very, 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 very infrequently. But when it does, it's a deadlock. And the best thing you can do is probably reboot the system or something, or kill off thread A or B. Okay, and this kind of situation was very common in the early days of Unix. Basically, there were lots of these kind of deadlock cycles in it, and we like to joke about modern operating systems like Windows got rebooted, right? Control Alt Delete, which you learn, I guess now, by the way, babies learn about Windows 10 according to these new commercials. If you learn this, the future will be easy for all kids, and they show babies running around and so on. They will not have to worry about difficult interfaces. They will not have to worry about how to reach in and process the web. They will not have to worry about World Hunger and Peace and all that sort of stuff because there is Windows 10. And I have to say, of all of the most recent commercials, that whole thing is it's hilarious to me. I'm not sure. Hopefully these kids are dealing with Windows 11 by then. But anyway, the point of all of this is basically that deadlocks are common and they're things that people have to figure out how to deal with. And basically, they always occur with multiple resources, and you can't deal with them by decomposing them. So if I were to just look at thread A, I have no clue, right? There's no deadlock there. If I just look at thread B, no problem. If I just look at the usage of, say, X, there isn't really a problem because it's part of it. You got to look at the whole cycle. And so, simple examples. You got system 2 disk drives, 2 threads, and each thread needs 2 disk drives to function. And, each thread gets 1 disk and waits for the other, and now you're deadlocked. So there are many situations you can come up with. Here's another one. This is the, I don't know how many of you have ever driven along Route 1. Lots of fun, beautiful coastline, lots of places where one of the lanes is gone, and so there's a single lane. Okay, this is very common. You get these signs, a few feet ahead, danger or 1 lane ahead, right? And, this is a situation where you can say, well, every segment of this road is a resource, and the car must own the segment under them, and you have to acquire the segment they're moving into. And for the bridge, you have to somehow acquire both halves of the bridge in order to make it across. So I'm assuming there's 2 segments in here. And this basically means traffic only in one direction at a time. And the problem occurs when 2 cars have been in the situation you got here where each has half of the bridge. And what do you do? Well, if a deadlock occurs, you basically can resolve if one car backs up. That's the idea of preempting resources and rolling back. And of course, in this situation, several cars may need to back up. Starvation is possible here where if you got one eastbound traffic is just going or north-southbound traffic is just going so fast, maybe nobody in the other direction ever gets to go. Okay? Other ways of resolving this, I don't know, Godzilla comes down and grabs the car that's in the way and lets the other one go through, right? There are lots of these resource contention sort of issues in life, and you're pretty used to them. I wanted to give you one that's a little bit closer to reality here, the actual computer reality. So there's a lot of networks that you use sort of that are inside of big servers these days, which are wormhole-rooted networks. And the idea here is that we actually we have an X, Y set of coordinates, and if you think of messages like trains, what happens is, a train may get to a corner and needs to go in a certain direction, and while it's on the track, it's taking up those resources, and you end up with a circular dependency here because this train, for instance, is trying to go south, this train is trying to go east, this one wants to go west, this one wants to go north, this one wants to go east, and they're basically stuck there because the next step is stuck, right? And basically, this is a multiprocessor network problem. And what's interesting is you can imagine fixing this by guys all caught that train there. Don't miss it. So we can start fixing deadlocks by basically disallowing certain turns. So this is a great example where, a cycle is a problem. Let's make sure that those two turns are not allowed. Okay? And so that basically says that a train in this scenario, or a message really, is never allowed to go north first and then east, or south and then west. Basically, all of the west and east direction has to happen first and north-south second. If we do that, then we have a deadlock, because there's no way to get a cycle. Okay, so you can actually prove in situations like this that there is no deadlock. And basically the proof is, those two curves don't exist, and if we had an imagined deadlock, any real deadlock, or any deadlock we had would involve one of the disallowed terms, and therefore deadlock is impossible. It's sort of proof by contradiction. And there's lots of systems that are designed this way to make sure that deadlock never occurs by preventing it. Alright, so first ask any questions on this, and then I'm going to go back to our previous deadlock. There was a couple previous. Does this make sense, everybody? So I prevented deadlock from happening by ruling out two of the terms that could allow a cycle. Yeah. So what's interesting about a train going straight is that the only thing it could be dependent on, say it's going straight east, is a train that, let's say it's only dependent upon this train going north-south, okay? But in that scenario, we know that north-south, this is its last leg, because it can't turn anymore, because that's disallowed. So we know that train will get to its destination and be absorbed, and that'll free up the guy going straight. So straight is never an issue here. It's always turning that's the issue. Okay, and then the assumption being that once the train reaches its destination, it gets absorbed into the destination. Okay, so can anybody tell me how to prevent this kind of deadlock? What is a use of resources guaranteed to prevent this kind of this deadlock from happening? Yes. Exactly. Perfect. Always acquire resources in an order. X, then Y, then Z, then W, then however they mix it up afterwards. Great. Okay, that is a constraint. Always acquire resources in an order. And in fact, if you look at the training, what we're really saying is always go, do your east-westness first and then your north-southness. You're doing those in order, and as a result, there are no cycles. Does everybody understand that fix? The fix was impose an order on the resources that you grab, and this as a result prevents you from getting in deadlock. Okay. And I encourage you to imagine that there is thread A and thread B are in a cyclic loop and try to figure out how that would work if they're all requesting X and then Y. You'll find it's impossible. Question, yes. How will thread B know which order thread A acquired it is a good question. What's the answer? Yes. Great. Yeah. decide in advance what the global order is. Okay, so thread A and B know because they were told never acquire resources in any order other than X, Y, Z. Yeah. Good. Okay. So I want to give you the dining lawyer's problem. There's 5 chopsticks. These lawyers are meeting for Chinese food. And there's 5 of them, and there's only 5 chopsticks. It's a really cheap restaurant, and there's a chopstick between each of them. Okay? And you need 2 chopsticks to eat. Okay? I don't know if we have any such restaurants in downtown Berkeley, but we'll assume for a moment we might. And what happens if they all grab them at the same time? They each get 1. Well, you start suing, I guess. That's deadlock, right? Because you need 2. And so the situation where they've all grabbed 1 is a problem. Now, by the way, you've probably all heard of this. It's the dining philosopher's problem. We're lowering ourselves to the dining lawyer's problem here. So, how do you fix the deadlock? Well, one option would be to make one of them give it up. That's probably not going to happen too likely, but one of them gives it up, eventually everybody gets to eat, because one person now can get 2 of them. They eat. By the way, you have to get past the sharing the chopsticks thing. Maybe they're really friendly lawyers, I don't know. But, one gets 2 chopsticks, they finish, and now they put them back on the table, and now we can make progress, right? So there's got to be some way to code this problem in a way that could make us be able to solve it in general if we had a situation where there are only 5 resources and 5 threads, and each thread needed 2 of the resources to make progress. Okay? You can kind of see where this is going. And I can actually tell you this. Never let a lawyer take the last chopstick if no hungry lawyer has 2 chopsticks afterwards. Okay? So that says that basically one lawyer is never able to take the last one if that's going to prevent somebody from having 2 who hasn't eaten yet. Okay? Now, it's not very satisfying. It's a bunch of words. It's like, well, where did you get that from, Cookie? Well, you kind of made it up on the fly, right? So let's talk this through a little bit more, because I always hated solutions to problems that were sort of word related, because you sort of get this feeling like I sort of understand it, but I'm never quite sure why. So let's dig into this a little deeper, right? So first thing we need for deadlock is we have to have mutual exclusion, which basically says that only 1 thread at a time can use some resource. Or in this case, the lawyer case, only 1 lawyer at a time can use a particular chopstick. Or in the resources we're talking about with the roads, only 1 car can use a segment of road at a time. Does everybody have the mutual exclusion idea here? Now I'm not applying mutual exclusion to blocks of code, but rather to resources. We also have to have the requirement to hold and wait, which basically says that a thread holding at least 1 resource is waiting to acquire additional resources held by somebody else. Alright, now remember that cycle I showed you at the very beginning? We had a thread that's holding 1 resource and waiting for another, right? Okay, hold and wait. The next one is that it's not possible to preempt. So if somebody's holding a resource, you can't tell them, give it up. Okay, that's not an option in this, if we're interested in deadlock. And finally, there's a circular wait, which basically says there exists a set of waiting threads, T1 through Tn. T1 is waiting for a resource held by T2, T2 for T3, so on, Tn for T1. If there's a cycle, and we have all 4 of these things, we might have deadlock. Okay, so these are necessary conditions, not necessarily sufficient. Okay? You have to look, because you could have this cycle, and it's possible that somebody else has got a resource they're going to toss back into the pot, suddenly T1 can go without waiting for T2's resource in our cycle to solve. Okay, so this is necessary but not sufficient. Question? Okay, and ignoring, the introduction of subscripts and so on, this is pretty basically just that graphical model I showed you earlier with the cycle today. Okay? Okay, somebody asked me a question. Everybody good on this? Makes 100% say? So let's look at how we can use this idea. So let's make up a resource allocation graph here. So we have a set of threads, which I'm going to have as little pink circles with a T number in them. We have resource types, R1, R2, R whatever. So a type is a box, and inside the box is a number of dots which represent how many identical things do we have in that of that resource. So this basically says we have one resource, one thing, but three resource, two things, and they're all identical. And so basically a thread could use any one of them and it wouldn't care. Okay? And so each thread utilizes a resource like this: request, use, release. Boy, that sounds like acquire and release of a lock, right? But now we're talking about resources in general. And we can build a resource allocation graph which has threads and resources. And you guys saw that very first slide we did in this topic. A request edge directed from T1 to R1 basically says that T1 is waiting for a resource RJ. And an assignment edge going the other way says that resource J is owned by piece of I. Okay, and just let me show you this just so you know. Don't get hung up in the notation, right? It's very easy to get hung up. Here's a graph. So what does this say? What's T1 waiting for? What's that? R1, great. What's T2 waiting for? Okay. What resources does T2 own? R3 and R1. Okay? Everybody with me? T3 owns one of the R4s. R2 is waiting, it's basically owned by T3, so it has an R4 and an R2, so on. Okay? And so here is a deadlock. Now how do we know that? Let's take a look. Notice that T1 is waiting for resource 1. Resource 1 is owned by T2. T2 is waiting for resource 2. Resource 2 is owned by T3. T3 is waiting for R3, one of the R3s, but both of them are owned by things that are waiting on T3. So if you were to work your way through this multi-cycle thing, you'd see that basically this will never resolve itself. There's a deadlock. Okay, questions? How many people are not sure this is a deadlock? Let me show you just to confuse this. Here's the cycle. Look, T1 is waiting for some R1. R1, one of the R1s is owned by T3. T3 is waiting for R2. One of the R2s is owned by T1. There's a cycle. Why is that not a deadlock? Anybody tell me? Yes. Okay, so walk me through why this will eventually finish. Okay? Great. That's right. So we can see that both T2 and T4 can eventually finish because they're not waiting on anybody. They put their resources back and suddenly T1 and T3 go. Okay? So notice that these graphs are actually kind of useful in that they can tell us, if we look hard enough, whether there's a deadlock or not. The problem is that, the first time you probably see this middle one, it's hard to tell there's no deadlock there. I mean, or it's hard to tell that there is a deadlock there because you're sort of tracing, and this other one maybe you can't tell that there's no deadlock there. Can somebody tell me how we might actually give it a graph? Oh, go ahead, quick. Give me an algorithm for figuring this out. Okay. That's almost good. I'll buy that as close. Okay, you guys are thinking too hard. Well, let's go back to this thread, this basic situation where we have no request arcs going out. So go further with that. So because T2 has no request arc, what can I do with T2? I can presumably finish it, right? And then I can put that resource back in the pot, and I can now look at the request arcs and see if that allows some thread to go that it couldn't before. And I keep working my way through a list. All right? So basically what I want to do is I want to come up with an algorithm that basically allows me to sort of simulate the threads to see whether there's a deadlock. Okay. Yeah, question? Yeah. Yes, but this is going to get, it's kind of hard to show for sure. But this simulation thing is a little easier. Okay, and I'll actually show you an algorithm in a moment. So let's just talk about methods for handling deadlocks, because I think this is very interesting. Suppose your system is in deadlock. So one thing you can do is allow the system to enter deadlock and then recover somehow. First of all, you have to have a deadlock detection algorithm, which we've been kind of working on. And then you have to have some technique for forcibly preempting resources away. Right? And basically, by the way, when you try to forcibly preempt resources, usually that's bad, right? Because the fact that some thread is holding onto a resource is because in order for it to work properly, it needed that resource. And think for a moment about mutual exclusion and locks. If you put a lock around some critical section and you forcibly remove the lock and give it to somebody else, I guarantee you that your algorithm is now broken. If it needed the lock in the first place, right? So, another is basically make sure the system never enters deadlock, and you have to somehow monitor all the lock acquisitions and so on, and selectively deny those that might lead to deadlock. I'll actually show you how to do that in a second. Or, you can ignore the problem and pretend that deadlocks never occur, and most operating systems do this, and when your system starts behaving strangely, what do? Reboot. Yes. You guys have been all well trained. Okay, so unfortunately this is kind of what often happens. Now how many people have taken 186 or a database class in general? What do databases do that are allowed along the lines of the first one? What would a database do? Yeah. Well, they've killed the one that's been running for the most time, but you got to make sure you still have correct behavior. So what do you need in addition to killing? Yes. Okay, so strict two-phase commit can be used to make sure you never lead into deadlock, but if you want to do something that might lead into deadlock, what can you do? Yes. But what can you do if it's already gotten into deadlock? Yes. Okay, you guys are missing the roll back to state, right? So the key thing that databases have is they have the ability to roll back. And so you can roll things back to before the deadlock and redo it again. And that's what often happens. They detect deadlock and they do rollback. Okay, so let's get this algorithm out here. And I just wanted to show you since you guys all figured this out already. So basically we're going to have three vectors. Okay, and what the vectors look like is a vector of free resources, which is the current free resources of each type. We're going to have a request vector of request from thread X and an allocation vector for resources held by thread X. And here's what we do. We first say that the available resources are equal to all the free resources. So free resources, for instance, there aren't any here because all the resources are taken. And so because there are two resources, this is basically going to be a vector of two things. So available resources are going to be 0, 0 in this vector initially because there's nothing free. Okay? And then we're just going to go through a loop after we take all of the nodes, all of the threads, we put them in an unfinished list, and we go through, and we basically do what we said earlier. For every node in that list, we say, gee, if the requests that that node has, which are the outgoing arrows, are less than or equal to the available resources. So for instance, if T1 is requesting 1R1 and 0R2s, their request vector would be 1, 0. And if I have at least one R2 in some situation, then I'll remove the node from the unfinished list because we'll assume that it's
Okay. That's all for this afternoon.